All right, let's sketch some graphs. We'll take everything we've talked about in chapter 3 basically so far and put it together so that we can sketch graphs without the use of a calculator, okay? So 3.6 covers sketching of graphs. Here's kind of like my process. First thing I do is I try to find the y-intercept in the roots, okay? So to find the y-intercept, you let x equal 0. Pretty easy. You can see where the thing's going to cross the y-axis. For the roots, we set the entire equation equal to 0, and I'll solve for these if they seem easy enough to do. If it seems like it's going to be really, really difficult, I typically don't worry too much about them, okay? But the more points we have, the better the graph is going to look. So I typically do, what I call non-calculus stuff first. I find the intercept, I find the roots, and if we're dealing with a rational function, x is in the denominator, I'm going to look for asymptotes. If we don't see x's in denominators, typically we're not dealing with asymptotes, okay? None of that stuff requires derivatives, so I typically look at that stuff first. Then I move into the first derivative. That gives me information about where f will be increasing, decreasing, and it'll help me find any relative max or mins. After I get that information, I then move on to the second derivative, where I'll get information about the concavity and points of inflection of f. Then, between steps 1 and 3, I now perhaps have some points. So in step 4, I plot all the points we just found. Then in step 5, I apply carefully the increasing and decreasing behavior of the function, and then finalize it with concavity at the end, okay? So let's go through a few examples of sketching curves and see if we can do this stuff, okay? So in the first example, we have a polynomial, okay? Again, you should be able to recognize a polynomial when you see one. That's not going to have any asymptotes, okay? So first thing I'm going to do is find the y-intercept. So I'm going to look at f of 0. I'll plug 0 in for x, and here we're just going to get back 0. So the y-intercept is the point 0, 0. I'm then going to look for roots. I do that by setting the equation equal to 0. Here we can factor. Excuse me. Should be 3x plus 4. And here we get x is 0, x is negative 3/4. So the x-intercepts, or the roots as we call them, 0, 0, and negative 3/4, 0. Okay, so we got a couple of points. I'm just going to kind of highlight these. Okay, and again, with a polynomial, we're not going to worry about asymptotes. Okay, now we'll move into the first derivative. So let's look at f prime. That should be relatively easy here. At least taking the derivative shouldn't be any big deal, okay? So we get that, and what are we now going to do? We're going to set this equal to 0 and look for critical points. Now again, I can factor this, and it looks like we're going to get x is 0, x is negative 1. There's our critical points. So I'll go ahead and do the first derivative test around those points. Okay, let's see. If x is less than negative 1, and again, I'm going to use the factored form. If x is like negative 2, that's going to be positive times a negative. So in this region, the derivative is negative and function is decreasing. Okay, I'm going to take a number like negative 1/2. Let's see, negative 1/2 squared is positive. Negative 1/2 plus 1 is positive. So the first derivative is positive. We are now increasing, and it looks like we just found ourselves a relative min at negative 1. We'll get the y value in a moment. Now if I take a number larger than 0, that's positive times another positive. We're still positive. The function is still increasing. So we're not going to have anything fancy at x equals 0 in terms of a max or min, but we do have a relative min at negative 1. How do we get the y value? Go back to the original function, right? So I'm going to look at f of negative 1. And look, use a calculator if you really need to here. You want to speed things up. Okay, but this looks like it's going to be what? 3 minus 4 is negative 1, if I've done this correctly. Okay, so it looks like the point is negative 1 for the relative min. All right. Yeah, right. So we got all sorts of information about f prime, where it's positive, negative, and where our relative max and min are. Well, in this case, just a relative min. Number 3, we're going to look at the second derivative now. Okay, so I'm going to take the derivative of this guy. And that's going to be 36x squared plus 24x. So again, we want to see where the second derivative is positive or negative, so we'll set it equal to 0, and I can factor a 12x out of this. And we're getting 0 and negative 2/3 here. Okay? So those are the values we're going to test around for concavity. Those are the x values where f double prime is 0. And again, I'm going to test the factor form. If I take an x value less than negative 2/3, like -1, okay? Negative and negative, so that's going to be positive. And so our function will be concave up to the left of negative 2/3. Now, in between negative 2/3 and 0, like negative 1/3 would be a good value to use. Negative 1/3 times 12 is negative. Let's see what we get here. 3 times negative 1/3 plus 2 is negative. 1 plus 2 is positive. So we have this negative times this positive is a negative. We're concave down. And it looks like we have ourselves a point of inflection. And if I take a number positive bigger than 0, we're going to get a positive times a positive is a positive. And we're back to concave up. And we've got another point of inflection at x equals 0. Okay, because we had sign changes. So again, to get those y values, I'll plug both of those back into the original function. Well, again, when I plug 0 back in, we got 0. So 0, 0 is a lot of things. It's a y-intercept. It's one of our roots. It ends up being a point of inflection. At negative 2/3, this is where I'm going to just use my calculator here and punch that into the original function because your algebraic skills are not what's being tested here. Okay, so feel free, like I said, to use a calculator if you need to speed up some of these y values. And I'm getting like negative 0.592 repeating. And when I convert that to a fraction, I'm getting negative 16/27. Okay, again, about negative 0.59-ish. All right, so again, let me highlight all the points we found. We've got our relative min, we've got a couple points of inflection, and we've got some information up above here, the root and the y-intercept, okay? So step 4 says, well, let's plot all those points. So that's what I'm going to do. We've now got a bunch of points to work with, so I'm going to plot them. So I'll create a set of axes here. And let's see, we're dealing with 0, 0. Negative 1, let's see, we got a root at 0, 0, and then again at negative 3/4, comma 0. So I'm going to call this negative 1. And so right about there is negative 3/4, comma 0. Okay? We have got a min at negative 1, negative 1. So right down here. We've got a point of inflection at negative 2/3, negative 16/27. So I'm going to go, let's see, negative 3/4. Negative 2/3 would be a little less than negative 3/4. And then negative 16/27 was a little more than negative 1/2. So right about there, I'll put that point. And again, the 0, 0. So we've actually got 4 points and they're plotted. Now, I'm going to carefully apply some increasing and decreasing behavior here. Let's see, something seems a little bit off though with one of these points. That doesn't seem to look right. 0, 0. Let me just double check something here. Oh, that's what it is. You may have already caught it. That should not be negative 3/4. I was careless. That should be what? Negative 4/3. I had that backwards. So I'm going to highlight that point in purple. That was this one. Okay, negative 4/3 is a little less than negative 1. Okay, so it's going to be like right about there. There's that correct coordinate. Okay, that was this. This guy right here. Sorry about the confusion. Okay, there's the actual root. Okay, so negative 4/3, comma 0. Excuse me. Jeez, I'm all over the place, guys. Forgive me. Negative 4/3, 0. There's that root. 0, 0 is the other root. So those guys I did in purple. That's these guys, okay? The relative min I'll do in blue. That was negative 1, negative 1. That's this guy. And then the points of inflection. I've got 0, 0 already there. I need this other one at negative 2/3, negative 16. So left about 2/3, down a little more than a half. There we go. There's all my points, as they should be correctly plotted. So I apologize for that. So again, steps 1 through 3, we do some calculus, some algebra, we get a bunch of points, we plot them. Now I'm going to carefully go through and focus on this increasing and decreasing behavior. To the left, basically it's doing what? F is decreasing from negative infinity to negative 1, and then it's increasing. So lightly I'm going to kind of draw that. From the left of negative 1, it's decreasing, and I'm going to go through these points. That seems to work. And now we are increasing indefinitely. And that seems to work. Okay, so we're decreasing through our points and then increasing. Now I'm going to apply my concavity. To the left of 2/3, we should be concave up. So it's going to be decreasing, concave up, and it's going to look something like that. Okay? And now we're increasing concave up because, again, that was our point of inflection, the pink point. Okay? Now, between negative 2/3 and 0, we change to concave down. That's just in this little region right here. So we're increasing, but we're doing it concave down. That's what that would look like. And now, to the right of 0, we're concave up and strictly increasing, and that's going to look something like that. And I'll just put the arrowheads on the end there. And that is basically the graph of this polynomial. Okay, so I lightly do my increasing and decreasing, then I come through and finalize with a concavity. Okay, and there's a pretty good look at that graph without using a calculator. Okay, there you have it. Okay, next one up, we're going to do a couple rational functions here. So next, let's do y equals 2x over x squared minus 25. Okay, so this is a rational function. We have x's in the denominator. I would expect some asymptotes here. But first is first. Let's find the y-intercept. If I plug 0 in for x, I get 0 over negative 25, which is, of course, 0. So again, the origin happens to be an intercept for this one. Okay, for the roots, let's see. The roots, well, we get those by setting the numerator equal to 0. And that also gives the point 0, 0 here. Okay, so the root and the intercept end up being the same thing. Now, asymptotes, vertical asymptotes, when the denominator is 0 and not the numerator. Looks like we got 2 of them, plus and minus 5. Okay, those are our vertical asymptotes. And for the horizontal asymptote, we're going to look at the limit as x approaches infinity of this thing. And because it's a rational function, we can test just the one infinity. We don't have to look left and right here. Okay, and what do we got? As x goes to infinity, the highest power term is in the denominator, so this is going to approach 0. I'll write it as equals 0. So that's the line y equals 0. That's our horizontal asymptote. That's our x-axis here. Okay, so we got some stuff. We got the y-intercept, which is also the root. We've got vertical asymptotes at plus or minus 5. We've got a horizontal asymptote along the x-axis. Okay, so a lot of information there. I'm going to move into the first derivative now. So I'll call this step 2. And I'm just using dy dx notation because I'm using y up above. So we do have to use the quotient rule here, okay? Derivative of the top is 2 times the bottom minus the derivative of the bottom is 2x times the top all over the bottom squared. I'm going to clean the numerator up. Oops. And cleaning up the numerator, we're looking at negative 2x squared minus 50 over x squared minus 25 quantity squared. Okay? And so to find the critical points, we're looking at where the first derivative is either 0 or undefined. It's going to be 0 when the numerator equals 0. Well, if we try to take the square root of that, we get imaginary numbers. So there are no real numbers representing the square root of negative 25. That means this thing never equals 0. Okay? We're not dealing with imaginary numbers in this class this year. So if you get an imaginary solution, there are no solutions. Numerator is never 0. Okay? It is undefined, however, at, again, 2 places. Same place as the original function was undefined, again, at plus or minus 5. which ties right back to the lesson on differentiability. If a function is not continuous at these points, the derivative does not exist at these points either. Okay, so we got two critical points, plus or minus 5. However, both of them make the first derivative undefined here, which is why I'm using the letter u instead of a 0. Now let's test the sign of this thing. And again, with a little bit of insight, you don't have to work too hard. I notice the denominator is always squared. I don't care what I'm plugging in. If that's not 0, it's going to be some positive number down there. The numerator itself never equals 0. In fact, if you plug any number in for x, what's going to happen? We're going to get some number. We're going to square it, so it's going to become positive. I'm then going to multiply it by -2, and so it becomes negative. And then I'm subtracting another 50, so it becomes more negative. So again, a relatively quick analysis. And if you went through and plugged like 3 different x values in, you should get the same result here. But a quick analysis kind of shows this thing is always negative. Okay, this derivative is always negative. What does that say then about our function in general? It is always decreasing. It is what's called a strictly decreasing function from left to right. We're not going to have any relative max-mins. And from left to right, this thing will always be going down. All right, let's look at the third step, which is the second derivative. And over here is my cleaned up form of the first derivative. Okay, so I'm going to be taking the derivative of this, again using the quotient rule. Derivative of the top, not bad, -4x times the bottom. Minus, okay, derivative of the bottom, that's actually going to require the chain rule because it's a quantity to a power. Bring down the power, leave the inside alone. New power is 1. Derivative of the inside is 2x. And because we're doing the quotient rule, it was the derivative of the bottom, which is all that, times the top. All right, and there's the quotient rule, derivative of the top times the bottom, minus the derivative of the bottom times the top. All over the bottom squared. Okay, so the bottom is this quantity squared. If I square that again, it's going to be what power? The 4th power. Okay, and it's kind of messy, and we've got some cleaning up to do, but if you notice, this quantity does show up in every single term in the numerator and denominator. So if you think about it, like it's kind of like a common factor up top. If I factor out the x squared minus 25, well, from this term, I'm going to be left with -4x times another x squared minus 25. And from this big term, I'm going to be left with the -2, the 2x, and the -2x squared minus 50. All over our denominator to the 4th. But now I can cancel that with 1 power of those in the denominator. Okay, so this thing is able to be simplified. All right, and now let's see, I'm going to clean this up a little more. This becomes what? -4x cubed plus 100x. I'm going to make that a -4x out front. And when I distribute, I'm going to get a positive 8x cubed plus 200x all over the denominator cubed now. And so cleaning this up, it looks like 4x cubed when I combine these plus 300x over this thing cubed. All right, so there's our second derivative. Again, this is undefined at plus or minus 5, just like the original function in the first derivative were, and it equals 0 when the numerator equals 0. You can factor out a 4x. It's going to be x squared plus 75. That gives me x equals 0, and that's always positive. That's never going to equal 0, okay? So we have critical points at 0, plus or minus 5 for the second derivative. So we call that f double prime undefined, 0, and undefined. And again, let's carefully test some signs here, okay? If I take a number less than -5, let's see. Negative times a positive in the numerator is a negative. If this is less than -5, like -6, that's going to be 36 minus 25 is positive, and a positive number cubed is positive. So we got negative times positive over positive here. That's a negative, we're concave down. If I take a number like -1, okay? Again, -1 times 4 is negative. That's positive. -1 squared is 1. Minus 25 is negative. Cubed is negative. Well, that makes a negative over a negative, which is a positive. We're concave up. Okay? At x equals +1. 4 times x is positive times a positive. But the denominator, 1 squared is 1, minus 25 is negative, cube it is negative. So now we're negative, we're concave down. And finally, if x is bigger than 5, every one of our factors is finally going to be positive, and we're concave up. All right, so again, take your time testing the signs of these things. Be careful. Go slow. Find what works best for you. Now, we're looking at some points of inflection. It may seem at a first glance that we have 3, but we really don't. There's no point of inflection at plus or minus 5, even though concavity changes, because the original function is not defined at plus or minus 5. Okay, we have asymptotes there. So there's not going to be points of inflection there, but however, the original function is defined at 0. The second derivative changes sign at 0, so we indeed have a point of inflection at 0, comma, and again, that's 0, 0 for this problem if I go back to the original blue function. Okay, so we got that point of inflection there. All right, so again, we got a lot of information. We don't have a lot of points here, but we got a good amount of information. So let's put this together here. So here's my axes. Okay, the intercept and the root were both 0, 0, so I've got a point right there. I have horizontal and vertical asymptotes. So the vertical asymptotes were at plus or minus 5. Okay, so we got those. And the horizontal asymptote was y equals 0, aka the x-axis, so that's this. Okay, and again, the horizontal asymptotes really come into play as we go way out to the left and right. I'm not saying that's what the graph looks like, but what I am saying is that in the middle, it's okay that we have a point lying on the horizontal asymptote in that region in between. It's okay to cross a horizontal asymptote, you just won't cross it as you go left and right, okay? So we got our 1 point, we got our asymptotes. Now, the first derivative didn't give us any max-min, but it said from left to right, this thing is always decreasing, okay? And now let's talk about the concavity. Here's where we got to kind of try to put the fact that the thing is decreasing and the concavity together here. To the left of -5, I'm decreasing and concave down. Does this make sense? Should I be crossing over that asymptote out here? No. Like I said, in the middle region it's okay, but not in the ends. So that doesn't make sense. So, you know, use the asymptote as kind of like a guide here. The function is decreasing, and it's going to be concave down. It has to look something like this, okay? It's going to go down along this asymptote, and it's going to come out and ride along that back to the left. Has to be in that section. Now, from -5 to 0, we're decreasing concave up. So I'm coming down from the asymptote, and I'm decreasing in a concave up fashion till I get to my point of inflection. Now I'm concave down while still decreasing, and I let the asymptotes be my guide. Okay? And now in the rightmost region, I'm still decreasing, but I'm concave up. So I'm going to come down along the asymptote, and I'm going to end up riding along this asymptote. Okay? Can't possibly be down in here because that would be increasing from left to right. The fact that it's going down from left to right puts us up in that upper right region. And now we have a pretty good look, without a calculator, at the graph of this rational function. Okay? And look, from left to right, it is always decreasing. It's decreasing, then it's undefined. It's decreasing from left to right. It's undefined. It's decreasing indefinitely. Okay, so that's what we call a strictly decreasing function, even though there are these big jumps around the asymptotes. Okay? And let us try the next one. This will be similar. If you want to give it a try and pause it and then go through and see if you can sketch it, that's good. Okay. So once again, our y-intercept looks like it's going to be 0, 0, which is also a root. We're going to have vertical asymptotes at x is plus or minus 2 here. That's where the denominator is 0. If that was a plus 4, by the way, that would never equal 0. There would be no asymptotes. Okay, so just be careful. And then the horizontal asymptote, I'll look at the limit as x approaches infinity. And same highest power on top and bottom gives us a horizontal asymptote along the line y equals 3 here. Okay, so I got that, I got my asymptotes, and I got that guy there. Okay, first derivative using quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top all over bottom squared, clean it up. And that cancels out pretty nicely up there. And we get negative 24x over the denominator squared. Okay, so that will equal 0 at 0, and will be undefined at plus or minus 2. Okay, kind of like before, I noticed the denominator squared, so as long as that's not 0, it's going to be positive. And I'll look at the sign of the numerator. So if I have an x value like negative 3, negative 24 times negative 3 is positive over a positive. Our function's increasing. If I take a number like negative 1, let's see, negative 24 times negative 1 is still positive over a positive. So we're still positive, we're still increasing. Sometimes when that's the case, I'll kind of redraw it like this, just so I see it. It's still increasing. Okay, great. If I take a number like positive 1 in this region now, I have a negative 24 times a positive gives me a negative up top, and the bottom is always positive. So here we're negative, we're decreasing, and it looks like we found a relative max at 0, 0. And a number bigger than 2, let's see, negative 24 times positive number over positive is still negative, and we're still decreasing. So we got a relative max at 0, 0. We're going up from negative infinity to 0 and down from 0 to infinity. Just watch out for the asymptotes. Okay. Just clean this up a touch. And now I'm going to take the derivative of this. Derivative of the top times the bottom minus derivative of the bottom, chain rule. Bring down the power, leave the inside alone, reduce, derivative of the inside times the top, because we're doing quotient rule all over bottom squared, which now takes us up to the 4th power. And again, this x squared minus 4 appears in every term, so I can cancel 1 power of it from everything. Okay, instead of me writing how I'm factoring it out front, I'm just showing you I can cancel this way instead. Distributing. Negative 24x squared plus 96. Again, think of this and that as a negative 4x that we're multiplying by. So that's going to give us a plus 96x squared over denominator cubed. And we can combine the x squareds. 96 minus 24 is 72. And so we get 72x squared plus 96 over the denominator to the 3rd power. We can set the top equal to 0. You can try and solve that, but that's always positive. Okay, any value of x you plug in, that's always going to be positive. And it comes down to the denominator. So the only critical points are at plus or minus 2, where this thing's undefined. The numerator is always positive. It's going to come down to the sign of the denominator. If I take a number like negative 3, somewhere in here, negative 3 squared is 9, minus 4 is positive, cube it, it's positive. We're concave up. A nice number in between would be right at 0. The top is positive. Let's see, 0 minus 4 is negative, cubed is negative. That came back negative. We're concave down. To the right of 2, the numerator is going to be positive. If If I take a number bigger than 2 and square it, that's bigger than 4. Minus 4 is positive. Cubed is positive. Okay, so we do have some changes in concavity, but remember, the original function has asymptotes at plus or minus 2, so there are no points of inflection. Okay, there are no actually points here. Let's try to put everything together in the graph. So once again, let's see, looking back, we had an intercept of 0, 0. Asymptotes at plus or minus 2. And of horizontal asymptote up at y equals 3 this time. Okay? And now let's see if we can determine where we are based on what's going on. So f prime, f is increasing to the left of our first asymptote. So let's focus just on this region right here. Okay? So to the left of negative 2, f is going to be going up and, whoops, it's concave up. Okay, and it's concave up. So can I be down here, concave up? No, because I'll go through the asymptote. So it looks like I'm going to be up in this upper region where I can ride along the asymptotes and increase in a concave up fashion. In between the asymptotes, we're now concave down. And we go from increasing to decreasing. So again, this was a relative max right here. And we're increasing and we're decreasing. So it's going to look like that. And it's completely concave down. So it's just going to look like a U through that point. And we ride along the asymptotes. And finally, in the last region, we're concave up and decreasing. So we're going to be coming down from our asymptote and then riding along the other one. And there now is the sketch of your graph. Okay? So a couple examples with the rational functions, and now let's just do one more. And we'll look at the graph of f of x equals x to the 2/3 power plus 2. Sometimes you deal with, this is not a polynomial because that's not a whole number power. Okay, so it's just some function of x. Let's take a look. So let's see the y-intercept, 0. If I plug 0 in for x, I get back 0, 2. For the roots, I can set this equal to 0, which says x to the 2/3 power equals -2. And so I got to raise both sides to the reciprocal power here, the 3/2. Okay? And let's see. I don't know that we're going to have any roots of this thing. Let's see. And the reason I say that is because this is to take the square root. And can you take the square root of a negative number? No. Okay? So it doesn't look like there's any roots here. Maybe. Just going to double check. Okay. And we get what we get. Okay, great. Okay, so again, since we don't have a rational function here, I'm not too worried about asymptotes. As x goes to infinity, you know, the cube root of something squared is going to get infinitely large, so I'm not too concerned here with asymptotes, okay? Moving on to the first derivative. Well, what are we going to get here? 2/3 x to the -1/3. Rewritten, that's 2/3 times the cube root of x in the denominator. Now, will that ever equal 0 in the numerator? No, there's no x. So the derivative never equals 0, but it is undefined at x equals 0. Okay, notice 0 makes the denominator 0. So we have a critical point at 0. And if I take a number less than 0, if I take a negative number and I take the cube root of that negative number, it comes back negative. Okay? It comes back negative, and then when I multiply that negative number in the denominator by 2/3, it's still going to be negative. So if I plug a negative in, I get back a negative. It looks like the function is decreasing. If I take a number bigger than 0 and I take the cube root of it, that's positive times this positive 2/3 is positive. And we're increasing, and it looks like we found a relative min at 0, comma 2. Okay, again, I go back to the original function to get the actual coordinate. Okay, so the first derivative was undefined at 0, but the function exists there, and that's a min. Let's now look at the second derivative. And I'm going to use this. Bringing down the power, we get negative 2/9 x to the negative 4/3 power, or negative 2 over 9 cube root of x to the 4th in the denominator. Once again, we have a constant in the numerator. That will never equal 0, but again is undefined at x equals 0. And notice ultimately what I'm doing. I'm going to be taking that number x and raising it to the 4th power. So what sign is it going to be always in the denominator? Positive. What sign is the numerator? Negative. This thing's always negative. The function's always concave down. No points of inflection. Okay? Let's try to put the pieces together now and sketch this graph. So what do we have? We have the point 0, 2 as our y-intercept. To the left of 0, the function is decreasing. To the right of 0, it's increasing. That's this information. And now I'll apply concavity. It's always concave down. So it's going to look something like this. We're going to be decreasing concave down like this, and then increasing concave down as well. And the graph would look something like this, kind of keep going up on both sides indefinitely. Okay. And there you have it, folks. And why is this continuous at 0, but the derivatives don't exist? What do we have going on here? We've got a sharp corner. We've got two different slopes coming into the same point, which is why the derivatives were undefined. Okay? And there you have it, folks. So kind of a quick review of what you did last year, maybe a little more detailed, though, dealing with some of the functions we deal with this year. Okay? So if you have questions on